Now going to talk about toric dynamical systems. The lecture has several parts. I'll talk about toric dynamical systems, give a definition, say a few words about the name, go into a little more detail about the matrix tree theorem that I mentioned in the previous lecture. We're going to have some interesting ideals that start to show up. There's going to be also some toric varieties and also some really nice theorems as well. So we have all that to talk about. And once we have that, I'll be able to revisit the deficiency and deficiency zero theorem and sort of understand what they mean in the toric context. So that'll be nice. Then we'll talk about the work of Karin Gotterman. It's basically her work is why we're here today. That she's the one that really made that deep connection between the toric geometry and the chemical reaction networks. And then I'm going to take a classic example introduced by Edelstein in 1970 and just sort of trace it through papers that have used it and end up in a pretty remarkable place in one of Karin's papers. And then also end on some of the work of George Craken. And so that's the plan for this hour. So remember that what we have, and so this again is from, there's a paper of this name by Craken, Alicia, Ann, and Barrett in 2009. And so here's our system that we have. And so basically this guy is a toric dynamical system when it has a positive, so that means a steady state solution that with all positive entries. So I want a steady state solution and I want it to be complex balanced. Remember that this is the complex balancing one, so I basically want this vector that we get of all our monomials. When I evaluate that at the steady state, I want not only this to be zero, but I want to actually make this part equal to zero, so it's the complex balancing situation. And it turns out that there's two reasons for this name. Well, I mean, Barrett likes toric stuff, so that's actually probably the real reason why they chose the name. But, and toric varieties absolutely are involved. So from that point of view, it's really true. But it turns out that what happens is there are many differential equations that really don't involve chemical reactions. So calling it a chemical network is a bit of a misnomer. And the HIV model is an example. Of course, that's a biochemical system that involves cells, but there are things even beyond that that basically are systems that look like this. And so what I want to do is give a couple more examples of basically some of these systems, and then I want to at least begin to show you some of the toric varieties, and I want to do it, I'll do it in the context of a specific simple example, but that example will help us see sort of what the matrix tree theorem does for us. So that's the plan for the next couple of slides. And I'm going to start, so it turns out I've taught differential equations many times, and whenever I teach differential equations, this is one of my favorite models. It's the SIR model, and it's basically from epidemiology, a very simple kind of thing. So you have, S is the number of susceptible individuals who can catch the disease, I is the number who actually have it. And then this is a disease that's not fatal, and what happens is you recover, and once you recover, you have immunity, you're not going to capture it again, and so you have this. And then the system of equations is that, well, let's look at this one right here. So, how does the number of infected people, how does that change over time? Well, first of all, people get infected. So when an infected person meets a susceptible person, an infection can occur. And that's the number of possible interactions. But then only a certain number of the possible interactions can actually occur. And of the ones that occur, then only some of those result in infection, because that depends on how contagious the disease is. So there's a lot packed into that constant alpha. So that's basically sort of where you get infected people, but also, of course, the people basically recover at a steady rate. And so that's what that one, so you actually lose infected people just because they're getting healthy again. And then, of course, anybody that gets healthy, that's what this one is. And then, of course, anytime somebody gets infected, that's where you lose people from the susceptible population. So this is a really lovely model. And of course, when I did that in differential equations, I had no idea it had relations to this stuff. And in fact, the way that people think about it is they think about this as a so-called compartment model. That you have the infected people, the susceptible, the infected, and recovered. And it turns out there's several ways in which such a model is presented when you sort of look at papers in the literature. And sometimes they just write it this way. And so basically they don't really, they say that, people flow from this compartment to that compartment, but sometimes they don't bother to actually describe the flows. So that's one way it's presented. Now sometimes when they present the flows, they actually give the flows as the rates of change. And so, basically, when I'm flowing here, people are flowing out at that rate, and that's basically that differential equation. And then here, people are flowing into I at this rate, but they're flowing out at that rate. And of course, that's that differential equation. And then, of course, they're flowing in to the recovered ones, and that gives the final one. So that's one way that you see it in the literature, using rates of change. But it turns out that's not the only way, because, of course, when you talk about rates of change, sometimes you talk about sort of the absolute rate of change, but other times you talk about the relative rate of change. For example, in an exponential model, this guy is constant. And so, the people in epidemiology are very used to that, so they're used to thinking in terms of relative rates of change. And so sometimes you see it written this way, where that's the relative rate of change. And so this, this one, because of the relative rate of change, gives the exact same system of differential equations. And so, but that's different from the reaction model. Because the reaction model, we have three complexes and three species, and then basically you have this reaction produces the infected, and the infected recover, and this chemical reaction model produces exactly that system by the law of mass action. And so what's interesting is that the way to think about it is the compartment model is species based, whereas the reaction model is complex-based. And of course, what happens is in epidemiology, people use compartment models. And so that's the idea, is that this actually is a chemical reaction model, but that's not at all how the people think about it. And so when you're talking about these systems, saying that it's part of chemical reaction network theory, sort of misses the fact that people think about it in just a totally different way. Another example is from population genetics, and I should point out that this is an interesting field, and for example, Zvi's poster is one that talks about one interesting aspect of population genetics. Here's a quite different aspect I'm going to talk about. And so, the background here is, we have chromosomes, there's locations on them, and you can have different stuff at the same location. Those are called multiple alleles, there's different kinds of blood type or hair color, color of a flower. And so those are all alleles at particular positions on a chromosome. But of course, we're diploid. That means we have two sets of chromosomes. And so suppose at a particular position, there are two alleles that can occur. And suppose that in a population, they occur with certain frequencies. Well, then what happens is that because there's two, then the genotypes, when you have the two chromosomes and look at what's happening, you can either have AA, AB, which is the same as BA, and BB. And then these will have what are called Malthusian fitnesses, little a, little b, little c. And very crudely, if I take the log of the average number of offspring, that's what the Malthusian fitness is. And then the idea is that when you then go from one generation to the next, these frequencies will change. So you get a discrete population model. We're going from one generation to the next. And then, of course, you want to track what happens over multiple generations. If you do that for a long time and compress your time scale, you can turn this into a continuous model of differential equations. And so this I got from one of the papers on this stuff. And so here basically, so what's the rate of change of these frequencies? Well, what happens is that there's a gadget called the marginal fitness of A, because remember P is sort of the frequency of A, so you get P times its marginal fitness. Here, this is the marginal fitness of B, you get Q times it, but then there's stuff that is subtracted, and here you get the mean fitness of the population, and multiplied by P or Q. And it turns out this system of differential equations comes from a chemical reaction network. And the question is, huh? You know, why? And what happens is that there's a theorem that it's due to Hars and Toth in 1979. I learned this from one of Alicia's papers. And so basically what happens is it's the structure of these polynomials. And so what happens is that, notice that this is a difference of two polynomials, both of which have positive coefficients. So that's the first thing you look for, that on the differential equation, each one is a difference of two polynomials, each with positive coefficients. And then the one that appears with a negative sign in front, notice that the variable I'm interested in is a factor. And that's, in those two conditions are the necessary and sufficient conditions for this to come from a chemical network. And in their paper, they actually give a sort of a little algorithm that, you know, basically given this, you can actually construct the network, and that's the network you construct from this particular thing. So if you apply the law of mass action to this, with P is the, you know, the concentration of A and Q is the concentration of B, this will turn into that. But this is not how the population geneticists think about this. So, you know, they clearly have their own ways of sort of coping with this stuff. And so again, you know, the name chemical reaction network theory, you know, in a sense it covers this one, but it's not how the people think about it. And so I'm not really sure we have the right name in complete generality. And what happens is in the special case, when you have one of these complex balanced solutions, that's when they said, well, to sort of reflect this diversity of what's going on, let's use something that doesn't necessarily say it has to come from chemistry, it can come from other things. And so that's where you come up with the idea of a toric dynamical system.
Before you go, can you go back one sec? Can you go back one?
Yeah.
So does that thing generalize? Because there's sort of an obvious, from going from the first level of the chemical reaction up to the second, you could imagine the same thing. Instead of A and B, you had A, B, C, right?
This works in complete generality.
Everything goes through.
Yeah, this works for an arbitrary system of arbitrary many equations and arbitrary many variables, as long as each derivative is a difference of two polynomials with positive coefficients, and where the one with the minus sign is divisible. So it's got to be polynomials, and it's got to be divisible by the variable you're differentiating. So that's the general theorem.
Yeah, because you can always write it as a difference of two positive polynomials.
And that's true. And but then, so the question is, so in a sense, all the negative terms, they basically have a multiple. There are a multiple of the one you're differentiating. Yeah. And so let's do an example of a toric dynamical system. And so let's look at this one where I have three complexes and only two species, just A and B, and every reaction is reversible. And what we're going to discover is that if I make a generic choice of the reaction rates, it's not a toric dynamical system. But if I make a good choice, then it is. And it turns out that, because remember that here's our complex balancing system, and remember that basically I want just, and I basically want this vector right here, this phi of x star, and so I want that to be a solution of just this. So I basically need to understand what's the kernel of the complex balancing equations, and it turns out that the kernel is spanned by these particular combinations of the rate constants. Now that looks pretty nice. It's a pretty formula. So you suspect there is probably something combinatorial that explains the various, combinations of indices. And the answer is yes. And what happens is that each ki is determined by spanning trees of the graph, but not all spanning trees. I look for ones that have a unique sink at I. So these are, and so basically they're a spanning tree just in the sense of the underlying graph, but when I put in the directions, there's a unique sink that has no outgoing arrows. So, for example, when I look here, it turns out there's actually three spanning trees that have a unique sink in one, because I can have both arrows pointing to one, or I could have an arrow pointing here to one, or an arrow pointing here to one. And so there's the, what I have, because notice because you might say, well, couldn't I reverse that arrow? Well, if I reverse that arrow, see, then I'd have a sink there. So to have a unique sink at 1, that sort of forces this arrow to go this direction. Similarly right here, to have a unique sink there, once I have this arrow, I have to have that one. So there's only 3, and then notice that, and remember this is a complex 1, complex 2, complex 3. So notice that right here, see, I'm going from 2 to 1 and 3 to 1. That's that term. Here I'm going from 2 to 3, right there, and from 3 to 1, right there. And here I'm going in the opposite direction. I'm going from 3 to 2, 3 to 2, and 2 to 1. So in fact, this first line is completely described by basically these spanning trees with a unique sink at 1. The same happens for 2 and 3. That's what these other 2 lines are. And the matrix tree theorem says that the dimension of the kernel is the number of strong terminal linkage classes. So this is now for arbitrary directed graph. And the basis of this uses the ki, the analogs of the ki, for the I in each terminal strong linkage class. So what that says is that in the general situation, the kernel of this matrix A kappa, it's supported on the terminal strong linkage classes. And so that's the result we needed in the previous lecture, that if I have a positive solution, which makes this a positive solution, which makes all these positive, and so basically in the case of a complex balance solution, I have something that's positive everywhere, and yet this only involves the strong terminal linkage classes. These have to be all the classes, and that's where the weak reversibility comes from. So that's really nice. So we have a pretty good understanding of that. But right now, I'm just thinking about this equation right here. Now I need to bring in sort of, I don't want an arbitrary solution. I want a solution that looks like this, because that's what it basically has to come, from these monomials. And so let's bring that into case. So here's what we just analyzed. And so first let's think about, so before I actually work out the details, let's think about this from the point of view of the deficiency 0 theorem. And so what's the deficiency of this graph? Well, there are 3 complexes. It's clearly connected. And then basically, so I have L equals 1, and then here's the stoichiometric matrix. The 2, 0 means the 2 A's, the 1, 1 means the A and the B, and that, of course, the 0, 2 is the 2 B's. So basically, I'm just taking all the possible differences, and when you do that, what you just get is the span of that vector, so that's one-dimensional. So what I get is 3 minus 1, which is 1. So notice I'm weakly reversible, but delta is non-zero, and that, by the deficiency 0 theorem, I can't be in the case where all rate constants give complex balance solutions. So somehow it's, I'm not going to have, I might have some complex balance solutions, but that'll depend on the right choice of rate constants. And what's the right choice of rate constants? Well, that's the solution I need, which again means I need this guy to be in the kernel of my A sub kappa. And of course, that's what this vector turns into in this case, because again, those are the columns of the exponent vectors. So it's got to be a multiple. And remember, that was the kernel. And of course, these are all positive numbers. And so what that means is I have this equation. And so notice what this equation is. So it's basically that the first one times the third one has to be the second one squared. So that's the condition on the rate constant. So if I have, and so in fact what we'll see is that basically if I have this, and so right now I have as an implication, we'll eventually see it's if and only if. So basically if the rate constants satisfy this condition, that's going to be exactly when we have a complex balanced positive solution. That's exactly when we're a toric dynamical system. So what happens is that in a situation like this, if I just write that down, it's not a toric dynamical system unless I pick the correct rate constants, and that's the condition to actually make it a toric dynamical system. So let's see a bit more of how that really works out. And it turns out that what I want to do is point out that there actually are some toric varieties lurking here. And so again, remember that, so there's our system. And again, we want, a complex, balanced, steady state solution that satisfies that. And again, I'm just rewriting what we had on the previous slide. But now let's actually just do some elimination theory. So let's eliminate lambda. And if I eliminate lambda, I get sort of this kind of thing. Looks a little complicated. And part of what's happening is that I haven't used the fact that these guys are positive. Well, it's hard to say positive in the kind of algebraic geometry I do. But I can say non-zero in the kind of algebraic geometry I do. And to say it's non-zero means that I'm going to want to do a saturation. But before I do, so basically, see, that's sort of a deeply irritating thing, and I'm going to get rid of that with the saturation, because of course there's the guy we want. But also it turns out these guys are actually pretty systematic, because notice that it's basically taking one of the lambda i's and lambda j's and multiplying it by one of the xi, xi to the yj's. So basically, I just sort of take all possible sort of cross terms, and so these are actually pretty obvious things that I want, and of course that's also something I want. So now we do the saturation, and it turns out when I do the saturation, it actually simplifies quite a bit. Because, see, notice, even though this is something we clearly like, notice it has an extra factor of x2. So I want to get rid of that. This one has an extra factor of x1. And so, in fact, when you end up doing stuff, you end up with a very simple little ideal. And it turns out this actually is a toric ideal because if I treat the capital K's and the little x's as variables, this is a genuine toric ideal. And so there's our first toric variety. But then the idea is let's do some elimination theory. Let's get rid of the x's. That leads to this guy. And that's the one that defines when I have complex balancing. And that's a second toric ideal. So what's interesting is that we actually get some nice toric varieties out of this situation. And these are intrinsic to the situation. Earlier I gave an example that looked sort of toric, but that was an artifact of the simplicity of that system. Here, these toric varieties are intrinsic to what's going on. And that's really what the toric dynamical system paper does, is to really explore this in detail. So it turns out there's going to be three important ideals, actually. So we're going to, I just showed you two, but before we get to those two, we have to start someplace. And so again, this is the paper. For some reason, I like section 2. They picked a nice title. What can I say? and so here's the setup. That so again, here's our system with our variables. And again, I'm going to, in this case, I'm going to just write the rate constants that way, but I'm going to regard them as variables. So now I'm going to work in the polynomial ring with because remember, these are the concentrations of the species. Those are the rate constants. So these are now just all variables. And then for our directed graph, well, so the idea is that what do we want for our sort of positive complex balanced steady state solutions? We see that's going to give us, setting that equal to 0, that's going to say that we're complex balanced. And, like I say, I can't say positive, I can say non-zero. That's how you say non-zero in the ideal way. And so basically I take this ideal, take its saturation with respect to this product. And so that's our first ideal. And I'm going to use the notation, so that's the variety of an ideal, and when I write that, I mean the solutions whose coordinates are positive real numbers. And then what happens is that in this setting, if I take a positive solution of this ideal, then so basically so here so there's a positive, that's going to be a positive steady state, and here are all my rate constants indexed by the edges are also going to be positive. Then it turns out I exactly have a toric dynamical system. And the way this one is set up is that not only do these guys give a toric dynamical system, but this is the witness that proves that it's a toric dynamical system. So I get in a sense, I get the parameters of the system accompanied with the proof that it actually has a positive complex balanced solution. So that's really nice. But what we're going to see is that we can even do better. And the way we do better is we switch coordinates. And the way we switch coordinates is by the matrix tree theorem. So remember that, so here's the assumption I'm going to make for the rest of the lecture. I'm going to assume that I have a weakly reversible system, and otherwise we can't have any complex balanced steady states. And then here's sort of a generalization of what I was doing in the matrix tree theorem. So what happens is, so I is one of the complexes, and the sum is over all maximal subtrees of our directed graph with a unique sink at I. And I write that by saying this is a tree, and the down arrow means that this tree has a unique sink right there. And of course, we've seen an example of this. So that's exactly what we were doing here, that, in this particular case, K1 right here was built from all the trees with the unique sink at 1. And then, of course, remember also that the K of t is the product of the rate constants corresponding to the edges of t. So in fact, I should actually go back and look at that. So the kappa of t, again, says that for each one of these trees, I take the product of the rate constants according to the edges, and that's for this particular tree, that's the kappa t. For this particular tree, that's the kappa t, and so on. So all I've done is simply give a fancy notation that writes down basically what these ki's are in general. So another way to think about some consequences is that the matrix tree theorem basically guarantees that these guys are in this ideal C of G whenever I and J are in the same connected component of the directed graph. And then what that means geometrically is that if I have one of these solutions, then it actually satisfies these equations. Remember, those are the equations that we actually saw earlier, because those equations were exactly these equations right here. And so basically what we've done now is, or the ones right here. And so basically, those are now, showing up, as elements of this ideal, and they, they basically contribute to the equations I have to satisfy. So that's pretty nice. But what happens is that, what that suggests is that maybe I should think in terms of the capital K's rather than think in terms of the kappas. And so that's the next stage, is to, and also, well, actually, what I'm willing to bet is that's probably actually a capital kappa. So we actually are, that actually is a Greek letter, but I'm just going to write it as think of it as the capital K. And so anyway, we have, so instead what I'm going to do is, because again, I was working in this variety, I was in the polynomial ring where the kappas, rate constants are the variables. I'm going to switch to a ring where the capital K's are variables. So that's the important thing that they do in the paper, is make that switch. And so, because those guys are really pretty much the heart of the matter, so what I'm going to do is, switch from these guys to that. So I'm going to go to this ring right here, where, basically, I have two sets of variables now, the species variables, and now I have sort of the kappa for each complex. So I just take these guys right here, but then again, I want to saturate. Because again, I want, I'm trying to say, a positive solution, that's the best I can do. So I take this guy and saturate, and again, working in this polynomial ring. And again, that's the earlier example. So that's our first, so this is the second toric ideal. So, and of course, T is for toric. And so, so that's our second one. And again, that's exactly what we did right here. When we do the saturation, we got a much simpler ideal. And so from that guy, we're going to actually, get some interesting stuff. And so what happens is that the C of G ideal, the first one, was the way to say what's going on using the kappas. This basically says the same thing using the K's. And so that's pretty nice. And what happens is this genuinely is a toric ideal. It's prime and generated by binomial. So that's it's as nice as you can get. at least for me. And so there's our first ideal. But then we get a third theorem, or a third ideal, and we're also going to get our first toric theorem. But first, before that, I just want to remind us about some of the cool stuff we saw in the previous lecture. And so remember that if I have one of my complex balanced steady states, then the classical lecture says that, remember, in every positive stoichiometric compatibility class, there's a unique complex balanced steady state, which is also locally attracting. And furthermore, in this setting, that any positive steady state is actually complex balanced. And of course, positive complex balanced steady state, that actually says toric dynamical system. For a toric dynamical system, you have this wonderful behavior. And so what's the third ideal? Well, remember the second ideal involved the x's and the k's, so let's get rid of the x's and just focus on the k's. And so again, that's elimination theory. And again, remember, and then here's the notation I'm going to use, is that the kappas I think of as the variables. This is a specific choice of positive numbers. And so here, I have the ki polynomials, and this is just evaluating, the star just means evaluating that polynomial at my specific choice of the rate constants. And then of course k star is then just the collection of all these. And so toric theorem 1 says that that basically this is a toric dynamical system if and only if the corresponding capital K's satisfy these ideals here. And it turns out that this also is a toric ideal, and of course M is for moduli. And so the idea is that this theorem right here says that the positive solutions of this system of equations tells us exactly when we have a toric dynamical system. And so in particular, we call this a toric moduli space. And the virtue of this is we don't need a witness. So basically this guarantees the existence of a witness. But then notice what happens is that as soon as basically what that says is that if you have you have one of these systems, as soon as your rate constants satisfy this condition right here, it's a toric dynamical system. This theory applies. And so basically, when your rate constants land in here, basically you have all this gorgeous stuff that just flows out immediately. And so this is a really lovely result. In fact, it's so lovely, I'm going to prove it. And so rather, I'm going to prove this part. So the question is, why does this guarantee the existence of a witness? And so let's do that. So here's what we have, and I'm going to prove one direction. And so the idea is that suppose I have some choice of rate constant so that this guy is actually in the variety of this ideal. So I want to prove the existence of a witness, and and remember the witness has to, and in this case the witness has to land in here, and so in particular my witness needs to have positive, so it has to be a complex balanced solution with positive entries. So how do we do that? Well, of course, this is an elimination theory. So if I work over the complex numbers, I'm in pretty good shape because we have the closure theorem. And so, there's the variety of an ideal. Here's the variety of an elimination ideal. This is a projection map, and it has Zariski dense image. That's actually and again, that because I'm over the complex numbers, that's what the closure theory says. This is just classic elimination theory. So what I have is this map with Zariski dense image. But hey, these guys are toric varieties. There's a lot of, these aren't just random varieties. They're toric varieties, and that's because these are toric ideals. Because of course what happens is that, this image, we're in the affine setting, so the image is just, in general, going to be some constructible set. And so I don't know that the image is, even though it has Zariski dense image, I don't know that it's actually onto. But now these are toric varieties. So you think about it, well, toric varieties. Well, tori. These guys each contain a torus. And so in particular, this map induces a group homomorphism of the associated tori. So I have a map between two complex tori, which has dense image, but then just standard algebraic group theory says this guy's got to be onto. So the extra structure guarantees that I'm onto when I actually look at the torus. But, oh, remember that this was a positive solution. It lies in the torus. And so this guy right here, that lies in the torus here, and so that means that K star is the image of a point in the torus upstairs, and that gives, basically one way to think about it, it gives a point upstairs in the complex variety, so I've proved the existence of a complex witness. And that's what the classical algebraic geometry does for us. But of course I want, and of course here I mean complex in the sense of complex numbers. I want a real witness, but remember that K star is positive, and this is a binomial ideal. It's just some monomial and stuff equal to some monomial and stuff. So when I take absolute values, it's still a solution. And so when I take the solution, then this vector of absolute values still satisfies the equations. Notice that taking absolute values has no effect here, because that guy's positive. So when I take this solution, take the absolute values, it still satisfies the equations. But now, and again, these are non-zero numbers because they're in the torus. So there's my positive solution that, basically, so there's my witness to what's going on. So there's the proof. And so now the proof that's in the paper is actually a much slicker proof, but I wanted one that really illustrated just the classical theory, and that complex numbers are actually a nice way to think about it, even though I really am interested in the real solutions. So let's return to a previous example, and this will answer one of the questions asked earlier. That so when is this guy a toric dynamical system? And the answer is, of course, if I make a random choice of the rate constants, it won't be. But in this case, here's the when I set stuff up, here's the the first one, the first toric ideal. Remember, this is the one that basically, gives the, in a sense, the rate constants and the witness, and this is the one that just basically says what do the rate constants have to satisfy. And so, sort of putting this together, again, we get this very pretty result that, this system is a toric dynamical system exactly when this happens. So when my positive rate constants satisfy this, I know the theory guarantees there's going to be a positive complex balance solution that makes this work. Now here's an interesting observation, and because this is a system we looked at earlier, and earlier we computed its deficiency. And so if you remember, we actually did that back here. And so, so right here, we computed deficiency, we found it's 1, just for that system. And so remember, the deficiency theorem doesn't apply. Deficiency is 1. And so what that means is that not all rate constants will give something that's complex balanced, but the condition that it be complex balanced, it's one equation. So in fact, this toric moduli space has codimension 1. So I have deficiency 1, codimension 1, and this is not an accident. And that's toric theorem 2. And so just remember what the deficiency is. It's the number of complexes, the number of connected components of the underlying graph, and the dimension of the stoichiometric subspace. And so to me at least, the intrinsic meaning of deficiency is that it's the codimension of the toric moduli space in sort of the space of all possible capital Ks. And that's just really lovely. And now we can actually revisit the deficiency 0 theorem, because remember that, so this is the theorem. It's complex balance for every set of positive reaction rates if and only if deficiency 0 and weakly reversible. And part of the proof is that, well, deficiency is 0. Well, by this toric theorem 2, that has codimension 0. That means it's got to be the whole space. But that means that this guy is complex balanced for any choice of K star. Because no matter what kappas I pick, they satisfy the system of equations because they're in here. And so basically, saying that the codimension is 0, giving us that says it works for all K star. And so we actually So I now have a proof that I believe. You know, of course, what I'm sliding under the rug is why is this the co-dimension, and that's why you have to read their paper. Now, I next want to talk about the work of Karen Gotterman because she's the one that really sort of started this enterprise of sort of toric geometry interacting with sort of the chemical reaction networks. And she did a series of 4 papers. The first one appeared in 2005, and the last 2 appeared in, the first one appeared in 2001, the last 2 appeared in 2005, and basically and tragically she died in 2005. Turns out I met Karen at this conference in South Hadley. That's where Jessica teaches. The conference is at Mount Holyoke. And I remember talking with her, and she was talking about her frustrations. You need funding to do this kind of stuff. And since she was very much the first to do it, well, the mathematicians thought she was too chemical. The chemists thought she was too mathematical. So it actually wasn't easy to get stuff. Of course, now the field is so established that seems incomprehensible, but when you're doing something new things are sometimes hard. But fortunately, she persisted and was able to do really nice work. I actually also interacted with this last paper because I'm on the editorial board of the Journal of Symbolic Computation, so I was the editor in charge of this paper, and unfortunately she died during the process, but we were able still to get the paper accepted, refereed, and published, which was absolutely the right thing to do. And in the Math SciNet review of this paper, Maurice Rojas writes that Karen Gotterman was a pioneer in computational algebra and extending its applications to differential equations, dynamical systems, and chemistry. Tragically, she succumbed to cancer at a young age on New Year's Day in 2005. She is sorely missed by her colleagues. It's a statement that's still true. And what I'm going to show is just some of the stuff she brought to the table in terms of this. And so, for example, just one quick thing is that I mentioned Toric Theorem 2. It turns out the proof uses a variation of the Cayley trick, and that's a trick that actually Karen and Wolfram use in the 3rd paper in their study of complex valence systems. And so, in fact, we'll see that some very contemporary ideas of people that are thinking about chemical reaction networks, we'll see some of those ideas are definitely in her papers. The way I want to illustrate that is to actually play with an example. So this is an example done by Edelstein in 1970. This is in the Journal of Theoretical Biology. And he proposed a biochemical model where you had A, B, C, and also L and M, and you had these reactions, but also you were keeping L and M at fixed concentrations by other stuff going on in the system. And the comment that Edelstein makes is that the system can have multiple steady states, so that's something they were really interested in. And of course, this idea of multi-stationarity is still a really interesting topic. So he said that this was a nice system because it could exhibit multi-stationarity, but it's analytically simple, so you could actually figure out what's going on. But he also pointed out that this has not been biochemically demonstrated. So this is not actually a real model necessarily that happens in the real world. It was something sort of pedagogical to illustrate what's going on. And what we'll see is it's a pretty good model. Now, and it turns out that in his 1979 lectures, so these lectures are online, they're really nice lectures if you want to learn more about this stuff from sort of the point of view of sort of the chemists working on it. This is a really nice place to start. And so what Feinberg did is he took the system and he sort of got rid of L and M, and so wrote it this way. And the question is, how do you get rid of them? Well, basically these concentrations are constant. So when you do right here, basically you have the rate of this, but how that's affecting A, it's going to be the rate of this times the concentration of L. But L is kept at a constant concentration, and so I'm just going to take that concentration and slurp it into the rate constant. And so that's what Feinberg did. He took the concentrations of L and M and just absorbed them into that one and that one right there. And then you get a system right here which models the behavior of this one. And Feinberg points out that this is a pretty funny reaction, since he comments that here I'm going from A to 2A. He says, you know, this is maybe like incompatible with the conservation of matter. And so again, he's recognizing.
Conversation of matter.
What?
Probably also conversation.
Oh, wow, conversation of matter. Matter talking to itself. Hey, this is, I got to write, this is my list of typos.
Yeah, his spell check ain't yet that one.
Yeah, I know. Oh, that's, thank
While
you.
you're at it, Malthusian was missing an L word.
Oh, yes, Malthusian, yeah. Yeah, it was Malthusian.
It looked like Malthusian.
Yeah, well, yeah. That's right. Oh, this is excellent.
Updating your corrections.
Yeah, if you do notice any other corrections, definitely email me. Yeah, but basically, you know, so he points out that, you know, this just doesn't work from a physical sense, but he says that, you know, but these sort of very simple, slightly unrealistic examples are really good because they illustrate what's going on. And so it's interesting that examples have been studied a lot, even though in some ways it actually is artificial, but we'll see that there's a lot of really fun stuff going on with it. And,
real quick, it wasn't a closed system though, right? Because you're holding them at fixed constant.
well, but again, what I'm doing is I'm replacing that with a different system that has the same behavior.
Yeah,
This is now a closed system.
yeah, but like
And it's like I say, these are different systems, but they have the same behavior.
so it's like a closed formal system.
Yeah, and the idea is that, you know, in one sense, because these are kept at fixed concentration, you know, there's other things going on to make that happen. And so Feinberg just says, let's dispense with that and just focus on this, because this is the essential thing. So again, he's taking one system, replacing it with another. And so this is the one that he ended up, and so the point is, you know, Edelstein wanted something that could have multiple steady states as analytically simple. This has exactly that. And in fact, the way that this system exhibits multistationarity is identical to how that system exhibits multistationarity. And so that's the thing he was interested in. And so again, because, you know, in math, lots of times you take something and you simplify it, and going from here to here is sort of a simplification. But as you point out, you know, some stuff is being swept under the rug.
Does the literature include some examples that are recognized, are biochemically?
The answer is that certainly some of the systems people have studied since then, I'm pretty sure are biochemically ones, and there's some pretty complicated ones. So like I say, this is just one particular example. Right.
It says it's not biochemically
Yeah.
demonstrated.
And it turns out that what happens is that for some choices of the rate constant, this is a toric dynamical system. And of course, when that happens, you know that every stoichiometric equivalence class, a compatibility class, is going to have a unique steady state. But for other kappas, the number of steady states in a given stoichiometric compatibility class can vary from 1 to 3. And so here's the picture, and it turns out that, and so basically, this is a case where the stoichiometric compatibility classes are unbounded. And so, you know, for this one that's sort of shown in the dashed lines in gray, you know, there's only one steady state, but the one in blue actually has 3 steady states. And so that's the stuff that can happen. And what I'm going to do is actually talk about both of these and go into a little more detail in each. And so so one question is, when is this guy a toric dynamical system? Well, the answer, of course, is we have the tools to answer that now. And so here's the system, and you know, there's the stoichiometric matrix, because we have, you know, 3. So we have 1, 2, 3, 4, 5 complexes and ABC, so we have 3 species, and so, you know, like the 2A here, you know, that's, you know, that's basically this vector and the A plus B, so that's the 3rd complex, that's the 1, 1. And then, of course, you know, how do I build, you know, A, you know, and when you work out, you know, you have to do a lot of differences to, you know, get the stoichiometric subspace, but when you sort of simplify it, you end up with just basically those 2 vectors actually span the stoichiometric subspace. And then when you play with the kappas, the matrix tree theorem, you know, it's pretty simple. You know, there's not a huge number of trees here. They're like pretty obvious. And then here's also, because I have to have a unique sink, you know, this guy has 4 trees, but one of them has 2 sinks, and so the other 3 trees give that. And so the kappas are actually pretty simple in this case. And so, you know, so here's the toric ideal, the first toric ideal, which I do this and saturate, and it gives this one. And then when I eliminate, I just get that. And so that's the one that defines the toric moduli space. And so basically it's a toric dynamical system. This has to vanish, but this in terms of the kappas is just that. So you get this very pretty condition. Exactly we know when this guy's a toric dynamical system. And just to check, notice that this is so that means that the toric moduli space, you know, the ideal has 1 generator, so it has codimension 1. And if you actually compute the deficiency, you know, the number of complexes, there's 1, 2, 3, 4, 5 complexes. There's 2 connected components. And the stoichiometric subspace has dimension 2, so I get 5 minus 2 minus 2, which is 1. So basically, this is completely compatible with you know, the fact that we found 1 generator for the moduli ideal. So again, the theory is just really gorgeous in this case. Now, I want to talk also about, you know, how to try to think about this in more general. And so the first people to try to really apply symbolic computation to this kind of situation was Melnick, Müller, and Noyne in 1989. And so there's their paper. And they treat this Edelstein example. But it turns out there's a typo. And it's embarrassing. I don't quite understand what they're doing in the paper. I mean, like, this is a paper using Grosvenor bases. Like, David, you should understand that. I don't. So there's basically either the typo completely messes up their analysis, or I'm just missing something of what they're doing. So it's one of those 2 possibilities. So I just redid it using what I would do if I had, you know, using Grosvenor bases. And so when you know, set up the differential equations, look at the steady states, and also I want this stoichiometric compatibility class, you get that. So this is basically, you know, so that's going to govern, so this is basically the steady states in this particular stoichiometric compatibility class. And their typo is they left off that exponent. And then it took me a while to figure that out. And so it's just computer Grosvenor basis. So here, I'm going to do something slightly different. And in their paper, they work over the function field of the kappas. And so rather than regarding them as variables, I'm going to slurp them into the coefficients. So that means that my kappas are very generic, one way to think about it. And so I just picked a Lex Grosvenor basis. And you get something like this. It's actually a really nice Grosvenor basis. And notice that it's cubic in x1. You know, it eliminates things as you'd expect. This is, well, it's just x1, and there's 3 factors here that are linear in x. That's just a constant. And notice that this is also, I'm treating this as a constant. It's just one of the coefficients, and so that shows up. And so that's a cubic in x. And then notice that the other 2 equations just tell me how to get x2 and x3 in terms of everything else. And again, because these guys are generic, I don't have to worry about that vanishing. So basically, you know, so once I figure out the roots of this, you know, I'll get steady states. And of course, I want the real roots. That's why I say there are 1, 2, or 3 steady states in each stoichiometric compatibility class. And so that's sort of what we saw before. And I could say a tiny bit thing, because if you take the discriminant of D, of that cubic in x1, you know, it's a large quadratic polynomial, and it basically involves the you know, the rate constants, but it also, if you think about it in terms of this C that appears in the system of equations, and so basically this one right here, the discriminant of this involves, it's going to be a quadratic polynomial in C, and it turns out that, of course, when the discriminant is positive, I have 3 real roots. It has 1 real root, the discriminant is negative. But if I look at the coefficient of c squared, indeed, the coefficient is that, which is negative. So that says that when c is really large, my discriminant's going to be negative, so there's only one real root. So this is sort of using symbolic computation to say that once I make a large compatibility class, I only have one real root. And this sort of is an algebraic way of explaining Feynman's picture, because see, the x2 plus x3, that really is where this plane, intersects the non-negative Orthant. And clearly, for some values of C, there are going to be 3 roots, and so there are some regions where the discriminant is positive, and others the discriminant is negative. And the point is that when C is really large, when I go far out, this guy's going to, I'm in the situation where I have only one real root. So that sort of is basically a symbolic computation sort of commentary on this picture from Feinberg. So that's pretty nice. But now to finish off, I want to talk about what Gotterman and Wolfram did in 2005 in their paper, because they study the same example. But they bring many more tools to bear. They bring a vastly different perspective to bear. And you'll see that the math just explodes off the page. It's just sort of mind-blowing. So here's our exact same guy. And, and here's our usual way of writing it. But what they wanted to do was to think about it in just a slightly different way. And so what they thought is, well, let's think of it in terms of, multiplying by these guys. So I think of, basically I take now a matrix with those as the column vectors, and then it's going to be that times this. So this is a slightly different factorization, one we haven't seen before. And then what they do is they take this and they basically set up these new variables. And these new variables, there's one for each reaction. So that's one thing that's different. We've done a lot of stuff with species. We've done a lot of stuff with complexes. In this approach, the reactions take center stage. And then what happens is there's 2 connected components. There's that one. So the first 2 reactions. So my reactions, I'm going to number them 1, 2, 3, 4, 5, 6. So I have 6 reactions. And then there's 2 connected components. And so for reasons I don't fully understand, they sort of put 2 different variables, x0 for one connected component, this for the other connected component. And I'm going to call these reaction variables, because they really correspond to the edges in our directed graph. And then, of course, when I take this system of equations, I can do elimination. And when I do elimination, I get something actually pretty simple. And again, Gotterman and Wolfram are regarding the kappas just as as arbitrary constants that aren't variable. So they're again part of the coefficients. So they're just working in this polynomial ring over this function field. And you get what they call a deformed toric ideal, because if alpha and beta were 1, that would be just the usual kind of binomials that can define a toric variety, but you sort of are deforming it with these alphas and betas, and you work out that alpha is this and beta is this. But of course, since I'm working in the function field, I'm perfectly happy with that. Now this ideal, let's think about it from the point of view of Grosvenor bases, and it turns out it has 4 Grosvenor bases, and you can calculate them using regular triangulations of a certain polytope. And of course the polytope, again, these are our exponent vectors, and you might say, oh, David, there's another typo. You repeated y4, and the answer is no, that's not a typo. Because basically these are really indexed by the reactions. And so, the first reaction, and the idea is that for each reaction, use the y vector of the source. And so, so for the first reaction, the source is there, so that's y1. The second reaction, here the source is it's y2. And what's interesting is that when I get to the fourth reaction and the fifth reaction, so the bottom one there and the top one there, they have the same source. And so that's why I repeat y4. And so again, I'm thinking of these in terms of edges, so y4 gets repeated. So I'm going to take a regular triangulation of this one, and I'm going to claim that it has 4 regular triangulations. And so there's the polytope. And again, the reason I put this here is because remember that Z4 and Z5, they correspond to the same vector y4, so that's y4 right there. Now you might look at this and say, David, I only see two ways to triangulate this, because you can basically, it's sort of a pyramid, and so basically I can slice the base by that diagonal or that diagonal. I only see two triangulations. Why do I say four? And the answer is that when you do this regular triangulation, you take the vertices, you lift them by certain weights, and then you take a lower convex hull. But because this one is doubled, I take two liftings. I take a lifting for Z4 and a lifting for Z5. And so what happens is that, what happens with these guys, the lower triangular, the lower convex hull is going to determine, whether do I take that diagonal or that diagonal. But here, when I lift them, whichever one, one goes higher, one goes lower, it's the lower one that I see. So I have two choices that can show up. So in fact, what happens is, so here's one of the triangulations that picked this guy, and it happened that when I did my stuff, basically I raised Z4 higher than Z5, so Z5 is the one that shows up. And so now I get my two simplices. Well, each simplex now gives me, a monomial. I can do, so one thing I can do with a monomial, well, that's a subset of reactions. So what I can do, so that says that I basically throw away reaction 4, I throw away that one, and I throw away reaction 6, which is that one. So I get this simpler system. And so, and so that's one simplex, and the other simplex picks out this one. So what's so what this geometry is doing is picking out some interesting subsystems, and one of the comments that Karen and Wolfram make is that multistationarity in the subsystem can persist to the whole system. And so what that means is that if I to understand multistationarity, I don't necessarily have to understand the whole system. I can look at some simpler stuff. For example, that's some recent work of Anne Shu and Timo de Wolf about trying to classify multistationarity in very small systems. And so, that idea that if you understand what's happening in the small stuff, I can tell you about big stuff. Here's this idea that they're working out very explicitly in this example in 2005. And then another thing is that in this situation, you actually get a Grosvenor basis. This regular triangulation gives you a Grosvenor basis. And how do you get the Grosvenor basis? Well, one way to think about it is, to get a Grosvenor basis, well, hey, that's a Grosvenor basis, but who's the leading term? So that's really what's important. And then the point is, remember when I did this lifting, those weights sort of determine what the term order is for the Grosvenor basis you want. So in this case, the fact that I got Z5, that meant I lifted Z4 higher, so that's the leading term of that guy. And then right here, one way to think about what's going on is when I do the lifting, I sort of get this diagonal that's lifted and that diagonal that's lifted, and which one's lifted higher? Well, whichever one is lifted higher, that means the lower one shows up in the lower convex hull. So that lower one showed up in the convex hull. That means this pair got lifted higher, so that's the leading term. And so that gives us this particular leading term. So we actually get a toric degeneration. So here we're seeing toric degenerations in a different context. On Wednesday we saw them in the context of geometric modeling. Here we see them in the context of picking out for this deformed toric ideal, deciding what its leading terms are.
And of course it's the same thing.
Yes.
Triangulation, geometric modeling are the same triangulation.
Yeah, which is like mind-blowing. And I'm going to mention that briefly on the next slide. But also what's interesting is that notice that here I have a linear thing in my Grosvenor basis. It turns out there's a theory that lurks behind that. There's some recent work of Elisenda Felu and one of her grad students, and that grad student is Angelica Torres's office mate. And they had one where they basically tried to analyze what's a situation that gives something like this, and they called it, it's the idea of when you have an intermediate. What's an intermediate? Well, an intermediate, it's two things. It's a species that shows up in only one complex, like C, for example. And to be an intermediate means that it's got to be sort of both a reactant, so it basically has to receive stuff. It also has to be a product. It has to have stuff going out. And so that says that, so that's an interesting gadget. But then, of course, what's related to that? Well, that's exactly Z4 and Z5, and that's where we get this linear term. So it turns out the fact that this is linear is actually no accident. And again, and I've mentioned 2 preprints. They were both posted in the archive this year. So here is work, current, contemporary, and it's basically very relevant to this example. So what this shows is that even though this example is pretty artificial, it's got a lot of juice. There is some fantastic mathematics going on here. And it also, again, it's just a tribute to the kind of insight that Karen brought to this whole field. That, you start off with a simple example, you have this pretty picture in, Feinberg, you look deeper, and my God, the stuff that's there is just mind-blowing. So like I say, we really owe a debt of thanks to Karen. But then there's, Frank's comment that, these toric degenerations, we have seen them before. So let me just say a few words about that. I don't fully understand the connection, so what I'm going to say is going to be pretty short. But just think about our system right here. But if I put on my geometric modeling hat, I see control points, I see blending functions, I see weights.
That's exactly how we think of it.
And I see, convex hull with some lattice points. And so we actually get this interesting map. And so there's a connection between this stuff and geometric modeling. I saw that, I just about fell over. Because remember yesterday in the panel discussion, I said that one of the things that surprised me were the connections. And this is one of the connections I just wasn't expecting. And to see the link, let's look at 2 papers of George Crakon. So one paper, he wrote a paper, in fact he wrote 5 papers with Feinberg. So that's the Feinberg of the chemical reaction network theory. He wrote a paper on multiple equilibria, so multi-stationarity, in complex chemical reaction networks. And first the injectivity property. So he did this injectivity property. Then a few years later, George with Luis and Frank did a paper on geometrical aspects of control points for toric patches. And one of the things they asked is this map injective? Because the idea is that, when you have, when you have sort of some funky control points, the map might be one-to-one, it might not be. And it turns out that one of the references for this paper is the work with Feinberg. And so there really is a link. So the question I have for Frank is, how did you link up with George?
I saw Feinberg give a talk about George's work in which he had a family of polynomial systems with these weights, which only had one solution.
Yeah.
And I recognize that. I mean, Luis and I have been talking about this a lot. We recognize that as well. Well, first of all, I'm interested in real systems and polynomial systems.
Yeah.
And so proving that there's always one solution was quite interesting.
Yeah.
Not more, not less accurate, but not more. And so I started with George. But we also knew this had to do with injectivity of parameterizations of patches,
right?
Which is an issue that will arise if people start parameterizing 3 folds and higher.
Right.
And we were led to both toric degenerations and triangulations. Right. And this injectivity.
Right. Yeah, because when they say some geometrical aspects, one was injectivity, one was sort of certain special kinds of degenerations, and I gather that.
Degenerations.
The generic ones. But then you did the subsequent paper that was the general degenerations, and that's where the pictures I showed on Friday came from, or on Wednesday came from. So it actually all links together. But let me just mention 2 other papers of George. So one is, he's one of the authors on the toric dynamical system, so you can now see why he was involved in that. And I mentioned this global attractor conjecture, and he has a paper on the archive. We submitted it in 2015. It's he has the most recent version is January 2016, so it's been there about 2.5 years. It's 41 pages, and parts of it have been submitted for publication. So it looks like that might be a proof there, but it has to go through the full mathematical process. So we can't yet say we have a proof of the global attractor conjecture, but in a couple of years we might actually have something more definitive. So so it's a really fascinating collection of material. So what I've hoped to do is introduce toric dynamical systems, appreciate Karen's contributions, just show you what happens when you have a really good example that you can illustrate a phenomenal amount of stuff. there's a lot more to say. There's a concept called detailed balancing that's a precursor to complex balancing. I haven't really said a heck of a lot about multi-stationarity. There's tons of work. There's all this, what's really going on with this global attractor conjecture. And also, sometimes you can, try to get information about steady states by certain invariants that vanish on them. So there's a lot more to go on, and we'll learn some of that from Alicia after lunch. So thank you. So any questions?
On slides 14 and 15, 14 and 19, have you any idea what the, okay,
Let me get back to it.
It's 19.
So there's 19.
okay, so this might do. What does the chemist or scientist say about the condition for toricity in the conclusion? So
So let me actually.
So that equation.
So let me actually go back to 14.
Yeah, that's the more complicated.
Yeah, and the reason I want to go back to that one is this equation actually appears in Feinberg's 1979 lecture. So this is something he actually worked out then. And so I don't know the answer to that question, but if you read, I think it's in lecture 2 he works this out, and if you read that, you'll find what he says about this. So that's what I would do. So my answer is ask Feinberg.
Okay.
So any other questions? So let's go have lunch.